Part 3, Current Carrying Conductors and Magnetic Fields. The motor effect. The third left-hand rule can be used to explain the principles of the electric motor. In a simple DC motor, remember DC stands for direct current, okay, so current from a battery, a loop of wire passes through a magnetic field. The ends of the loop are attached to something called a split ring or a commutator, which turns within the loop. Fixed brushes rub this commutator, which in turn is connected to a voltage source or a battery. In the diagram below, the loop on the right side is always forced down, and in the same way, the loop on the left side is always forced up. Okay, so let's talk a little bit about this. Okay, so we have the split ring right here. Now, the idea of the split ring is if that wasn't there, what would happen is that the current in the loop would kind of change directions. What we want is the current in the loop on the left side. We always want the current going this way. So, of course, as this thing spins, okay, the brush is touching this side first. You can kind of see my little drawing on the C there. Touches that side first, and as it spins, okay, of course, that side moves around this way. So this part of the brush, the right side, spins and now touches the brush. And now the electrons go that way again. So the electrons are always flowing into the page on the left side and out of the page on the right side. And it is that split ring that makes that happen. Okay, so now let's talk about our third left-hand rules. Okay, so in our third left-hand rule, remember, your thumb points in the direction of the current. So your thumb would point into the page. Your fingers point from north to south. So this will be your thumb. Okay, so then your fingers point this way. Wow. Okay, that's not a very good hand. But of course, the palm pushes upward or out of the page. Okay. No, just upward. Okay, so points upward, great. Then, of course, remember how this works is if the charges are moving parallel with the field, okay, so the magnetic field is going north to south. So as the electrons make this curve in the loop, there's no added force there, right? Because now the electrons are going parallel with the magnetic field. But as soon as they turn the corner, now they're coming out of the page. So your thumb points out of the page. Your fingers point north to south still. And now your palm is pushing down. Okay, so the left side pushes up. The right side pushes down. And you can see how that spins the loop of wire. I guess in this case, that would be a clockwise direction. Okay, and of course, this just keeps spinning and spinning and spinning. Now, initially, when scientists discovered this, it was like, oh, yeah, it spins. Okay, but the thing is, you attach gears to that, you attach pulleys, etc. Now you can make wheels move or gears spin, and you can make this motor do the work that powers so much of the modern devices that we enjoy. All right, so let's look at the mathematics of this. The magnitude of a magnetic force on a conductor can be calculated using this formula. So force magnetic is equal to ILB. Now, I kind of like to rearrange this every now and then, and just because then it looks like Bill. So you'll often hear me say, this is the Bill formula. Okay, anyways, don't get too caught up in that. It's just kind of a neat thing. Okay, so B, of course, is the magnetic field measured in teslas. I is the electric current measured in amps. L is the length of the conductor that is perpendicular to the magnetic field. So remember, the magnetic field goes one way. The length of the wire that counts goes this way. Remember in our little example up there, as the electrons turned the loop, okay, it was going parallel. Okay, remember that force didn't count. Well, it's not that it didn't count. It wasn't there. There was no force as the electrons went parallel with the field. And then when they turned around, oh yeah, 90 degrees again, Okay, now there's a force again. Okay, so we've got to be perpendicular to the field. Okay, and Fm, of course, is the magnetic force. Now, remember, the point of this course is not just to get you ready for your diploma exam, it's to get you ready for the next course. If the conductor is not perpendicular, then this formula, remember last time we also had a sine theta involved? Well, this time we still have a sine theta. That's for anything that is coming in at an angle. Now, that is not in our curriculum. That is for college and university, but you still need to know that it exists because, the magnetic field is there. What if the wire is coming in at an angle? So it's not parallel, but it's not perpendicular. There is still a force involved with that. You only get no force when you are parallel to the magnetic field. Okay, so anyways, there's that extra sine component for wires that come in at an angle. So remember, you don't really need to know the angle part, but this does explain why a perpendicular force is 0, because if the conductor is parallel, there is no magnetic force, and that's because sine 0 or sine 180, they are both 0. So if you are 0 degrees to the field or 180 degrees to the field, or it doesn't matter if the electrons are going this way. See, I'm drawing up here again, guys. So if the electrons are going this way, you're still parallel to the magnetic field. We said that was this arrow. Okay, anyway, sine 80, 180, sine 0 is 0, so no force. Fantastic. Moving on. Okay. Alternating current motors, AC motors, do not require the split ring, the commutator, because with AC current, the current reverses itself. Remember, it goes one direction for a little bit, the other direction for another. Okay, and that has to do with the frequency, like a 60 hertz would switch every second, 60 times per 60 hertz would be 60 times per second. So anyways, it flips back and forth all by itself. And that just makes sure that the motor, the electrons are always going the same direction on the one side of the loop of wire. Okay. Most of our electric motors are AC motors because electric energy for industrial and household use is transmitted as alternating current. So that's like the power lines that you see outside. Those are all AC. Okay. An example of a DC motor is the starter motor on a car. Okay. Comes right from a battery. Okay. So let's talk a little bit about galvanometers. And those are simply it's an umbrella term for electric meters, like a voltmeter or current meter, that kind of stuff. Okay, galvanometers are instruments used to detect electric current, or detect an electric current. A galvanometer may be calibrated to measure current, in which case it's called an ammeter. It may also be calibrated to measure potential difference. Okay, remember, potential difference is just voltage, and in that case, then it's called a voltmeter. These instruments also make use of the motor effect. A current-carrying conductor in a magnetic field will experience a magnetic force. This force is directly proportional to the current flowing through the conductor. This concept is used in electric meters, okay, as well as other types of meters, like speedometers in cars. Okay, galvanometers form the basis of all electric meters. Okay, in a galvanometer, current flows through the coil as shown above. So we got current flowing through this coil. And the thing is, it flows that way or the other way. It really doesn't matter. Okay, that part's not important. That's why they don't show you the battery for the current. Okay, the result is an interaction between the two magnetic fields, which causes the movable coil to rotate against a spring, resulting in a scale reading. It should be noted that a galvanometer will produce a full-scale reading with a very low current through the coil. Okay, a galvanometer is converted to an ammeter by placing a shunt or a wire of low resistance parallel to the coil. In other words, a parallel path for the electrons is provided so that only a small fraction of the electrons go through the movable coil. Okay, so we end up with electrons going through here. Now remember, this is like a solenoid, right? So this is going to set up an electric field. Okay, electric field, a magnetic field, sorry. Now remember, as your fingers wrap around those coils, okay, if it's coming this way, Okay, so you wrap your fingers around kind of like that, and your thumb points this way. Okay, so you'd end up with a north pole on that side. Okay, well, that attracts the coil of wire, right? So it goes this way. So all of a sudden, the coil, okay, then takes this the movable coil moves, okay, and that moves this against the spring, okay, and you get a meter, okay, or meter. You get the pointer points to a scale on the meter so that you can tell how much current was going through the coil. All right, awesome. Okay, good enough. Let's work through some examples. Number 1, a 0.222 meter long copper wire carries a conventional current of that much amps north through a magnetic field measuring this much vertically upward. What is the magnitude and direction of the magnetic force acting on the wire? Okay, now this example makes use of a word that we kind of just dropped last lesson. Okay, and that word is conventional current. Remember, back in the day, the scientists thought it was the positive things that moved. Okay, so whenever you see the word conventional current, we are going to be using our right hand. Okay, if they just say the word current, it's electron flow, so left hand. But conventional current, that is right-handed. Okay, awesome. So we have a length of wire. Okay, we have a current. We have a B. Okay, so FM equals ILB. That's the formula that's on the sheet. This is Bill, right? This is a Bill formula. Okay, so let's see. The I, 0.960 amps. The L, 0.222 meters. And the B, 7.50 times 10 to the negative 4 Teslas. Okay, so if we get our calculators out and just type that in, 0.960. 60 times 0.222 times 7.5 times 10 to the negative 4. 7.5 times 10 to the negative 4. So that is to 3 sig digs. Oh, sorry guys. There we go. That's better. Okay, so 960. I typed in 60. Haha, funny. Okay, it happens though. Okay, so anyways, that of course rounds to 1.60 times 10 to the negative 4 newtons. Okay, it's 1.5984 times 10 to the 4th, course rounding to 3 sig digs, 1.60. Okay, now that's the magnitude. Now we also need the direction. So what is really easy, if you go make a little compass, north, west, east, south, okay, then remember, then we have up and down as well. So we can come out of the page would be up, into the page would be down. Okay, so our current is going north, so we point our right thumb, remember right because it's conventional, point our right thumb north, okay, and then the magnetic field is going upward, so we point our fingers up out of the page, okay, and then we look where our palm pushes. And our palm, if we do that, so remember, right thumb goes north, fingers come out of the page, so our palm pushes east. So this is, whoops, sorry, weird. Okay, so this is 1.60 times 10 to the negative 4 newtons east. There we go. Sorry, I kind of messed up there we go. That's better. Awesome. Okay, number 2. A conductor 0.320 meters long is placed in a magnetic field of that. Assuming the conductor is perpendicular to the magnetic field, and the magnetic force acting on the conductor is that much, what is the current flowing through the conductor? Okay, notice how in this question there are no directions. So if there's no directions in the question, we don't have to worry about which direction the current is flowing. It's just flowing. Okay, now So again, this is a Bill formula. We've got a force, we've got a length of wire, we've got a magnetic field. Really, the telltale difference between the two formulas is going to be one will have a length of wire, whereas the other one will have a charge, like a proton or electron just getting shot or moved. Okay, so again, length of wire. So this is a Bill formula. So Fm equals ILB. Okay, and let's see. Now we have the current. Sorry, we're looking for the current. We have the force, 4.00 times 10 to the negative 2 newtons. We want the current. We know the length of the wire is 320 meters, and we know the magnetic field is 0.210 teslas. Okay, so we just do some quick rearranging, and we solve for I. All right, so let's just do that quick. Negative 2. And that one works out to 0. And what have we got here? 3 sig digs again. So 0.595 amps is what that rounds to. So there is our answer. Yay! Okay, number 3. 0.500 meter length of conducting wire is carrying a current of 10 amps, is perpendicular to an external magnetic field of 0.200 teslas. Determine the magnitude of the force on this wire. All right, well, that's pretty straightforward. That's just Fm equals ILB again. ILB. Okay, so the I, 10.0 amps, the L, 0.500 meters, and 0.200 teslas. Okay, so 10 times 0.5 times 0.2. Okay, and that is 1.00 amp. Whoops, funny. Amps, duh. Okay, it's a force, so 1.00 newtons. Awesome. Easy enough. Okay, number 4. This one's a little tougher. A thin conducting wire, 0.75 meters long, has a mass of 0.060 kilograms. What is the minimum current required in the wire to make it float in a magnetic field of magnitude 0.15 teslas? Isn't that interesting? Float. When you drop a wire, it falls, right? Why does it fall? That's an interesting one. See, on Earth, things fall because of gravity. So if we are going to make something float, we have to match its gravitational force just in the other direction, right? So if we draw a free body diagram on the wire, gravity is going to act downward on the wire. So we have to set up, in this case, we're running it through a magnetic field. So it's going to have a magnetic force going up. Now, if the magnetic force is stronger, this thing is going to accelerate upwards. If the gravitational force is stronger, it's going to accelerate downward. Okay, the only way to make it float is if the magnetic force equals the gravitation force. So in this case, this is an ILB, magnetic force, has to equal the mass times the acceleration of gravity, kind of thing. So, and this says what is the minimum current. So I'm still looking for the I. Okay. Wow, I don't think I did that quite right. No, I got like a capital L and a small L. Haha, that's funny. So I, there we go, LB. Okay, great. All right, so I'm looking for the I. The L is 0.75 meters. The B is 0.15 teslas. And that has to equal, look how this question was so nice and they gave us mass, 0.060 kilograms. And the G, of course, on Earth is 9.81 meters per second squared. Okay, so we do a little bit of algebra. Basically, we're going to divide the 0.75 and the 0.15 to both sides, and we get I equals, okay, so 6 times 9.81 divided by, Okay, and that works out to 5. Whoop, did that again. And let's see, we've only got 2 sigdigs here, so 5.2 amps. Okay, that's a really interesting consequence of that. So if we flow a 5.2 amperage current through this wire, yeah, it just floats in the magnetic field. That's kind of nice. Can you think of something else that floats that humans have made? How about the maglev trains over in Europe? Okay, those things are absolutely amazing, but right, we put enough current through those things. Now they float on top of the rails, and it's really quite interesting. Anyways, moving on. Sorry, a little aside there. Okay, a solenoid. Remember, solenoid electromagnet lies in a horizontal plane with a current balance. Okay, W, X, Y, Z balanced horizontally in the solenoid core at the point Z and W as shown below. So basically what's going on is you have this little balance pod. Okay, so this rectangle here that is in the solenoid, and it is balancing this little mass right here. Okay, interesting. Okay, so in order for that to balance, if you just let this thing, turn off all the current and everything, what ends up happening is that inside the solenoid, the little balance thing tips up and the mass goes like that. Well, when you turn the current on, there's a magnetic force pushing down on this, so you end up with a nicely balanced, see there's a magnetic force on that side, which makes the current balance work. Okay, so there's got to be a magnetic force acting down on this side. Okay, sides WX and ZY of the current balance are 7.10 centimeters, 7.110 centimeters. Okay, side YX is 1.90 centimeters. Okay, a current of 6 amps flows through the conductor on the current balance. If the mass of 1.76 times 10 to the negative 2 kilograms is necessary to balance the current balance, what is the magnetic field strength in the solenoid? Interesting. Okay, well, there's a couple of things going on here. Remember, this is a case, so we've got a force of gravity acting on the little mass, right? The force of gravity acting down, and that's going to be counterbalanced by a magnetic force. So that's very similar to the last question. So this is going to be mg equals ILB. Okay, that's nice. Now, here's the thing that's the kicker. You know the mass, you know what gravity is, you know the current, you want the magnetic field, and look, they give you a whole bunch of lengths. Now, you guys know enough from the second left-hand rule that when you have a solenoid rotating around like the coils, okay, it doesn't tell you which way the electrons are going in that coil, but you do know that the magnetic field is going to be going along the coil. So north could be pointing this way, or if the electrons are going the opposite direction, that could end up being a south pole and a north pole. Doesn't matter. Either way, the magnetic field is running this way along the solenoid. Well, there's a very interesting thing for that. See, this part of the current from Z to Y is going to be parallel with that magnetic field. Same with W to X is going to be parallel with the magnetic field, whichever direction it's going, north, south, or south, north. Okay, Z, Y, and X, W, those are going to provide absolutely no force because they are parallel to the magnetic field. So really the only distance that counts here is the part that's perpendicular to the magnetic field, and that is the XY, 1.90 centimeters worth. So this is the distance, the length we have to use in our formula. So hopefully that makes sense to you. The other ones are parallel. The 1.9 is perpendicular. That's a big deal. So the mass, 1.76 times 10 to the negative 2 kilograms times 9.81 meters per second squared equals my I. Well, we know that that is 6.00 amps. We know the length is 1.9 centimeters. So remember, convert that into meters. Okay, so 0.0190 meters, and now we can figure out the magnetic field. Okay, so when we do that really quick, so 1.76. So I'm just typing it in on the calculator. Okay, and then the magnetic field, I guess we can use the perpendicular sign. Okay, the magnetic field is 1.51 Teslas. And there you have it. Okay, so I would really like for you guys to practice this section. Starts on page 613, and I would like you to do number 1, 2, and then 7 through 11. You can go right out of your textbook, or you can print the PDF version from the card. That way you can write all over it. Anyways, thanks so much, guys. We'll see you next section.